Hello, everyone. Good afternoon, and welcome to our Moscow Telecommunications Seminar. Today, we will invite a new speaker, Aleksei Shashin. Aleksei Shashin has received his bachelor's degree in applied mathematics and physics from Moscow Institute of Physics and Technology in 2021. Currently, he is a researcher at Wireless Networks Lab at IITP-RAS and a master's student at MIT. Aleksei's research interests include 5G networks, ultra-reliable low-latency communications, link adaptation, and transmission parameter selection. Today, he will tell us about enabling URLLC in Uplink, technical realization, challenges, and approaches. So, Aleksei, the floor is yours.
Thank you, Ilya. Good evening, everyone. My presentation for today's seminar is about key features and challenges for enabling ultra-reliable, low-latency communications, or shortly URLLC, in 5G networks. It should be noted that the considered problem is different for uplink and downlink, and today we will focus on the uplink case only. This is the outline of my presentation. Firstly, I will tell you about technical realization of URLLC in the uplink. So we will consider the main features provided by 5G networks specifications. Then we will discuss the transmission parameter selection problem. In particular, I will review the solution from the literature and present an algorithm that was proposed in our recent paper. Let's start. First of all, what is URLLC? Ultra-reliable low-latency communications, or URLLC, is a novel traffic type that will be supported by 5G networks. URLLC imposes very strict latency and reliability requirements for packet transmission. Many novel applications, such as autonomous vehicle management or telesurgery, generate URLLC traffic in the uplink. For example, each autonomous vehicle should transmit information about its position or obstacles detected on the road. Similarly, during the telesurgery, the surgeon sends commands to the remote robotic manipulators that react to these commands with the corresponding action. Typical URLLC requirements are shown on the slide. And for detailed information of different requirements for different applications, please refer to the following documents. Specifications for 5G networks describe two methods for uplink channel access. According to the grant-based method, when the user equipment has data to transmit, it sends a scheduling request to the base station GNetB. The GNetB processes this request, select the frequency resource elements, time slots, and parameters for the user transmission, and sends a scheduling grant to the user equipment. Only after processing this grant, the user equipment can start to transmit data. As a result, the URLLC latency requirements may be unsatisfied because the start of transmission is too close to latency constraints. Another channel access method is called configured grant or grant-free. According to this method, the GNetB configures transmission parameters for user equipment in advance. Hence, the UE can start transmit data right after the packet arrival using the pre-configured parameters. This method significantly reduces latency in contrast to grant-based method. And the following studies show that the grant-free channel access provides a much better capacity of network with URLLC traffic than grant-based channel access. So next in the seminar, we will focus on studying the grant-free channel access method. When user equipment uses the grant-free method, the base station should configure in advance the following parameters: modulation encoding scheme, number of transmission attempts, periodicity, time domain allocation, frequency domain allocation, HRQ parameters, and frequency hopping. Let's discuss all these parameters in detail. To increase the transmission reliability, specifications of 5G networks introduce the new modulation and coding scheme table. This table includes 6 new modulation and coding schemes with the lower code rate and hence higher reliability than in previous MCS table. However, these MCSs have lower spatial efficiency. So it means that using them leads to an increase in channel resource consumption. Another mechanism that improves transmission reliability is the hybrid automatic repeat request, or HRQ. This mechanism allows user equipment to perform multiple transmission attempts of the packet, and the GNOD B can jointly decode all received transmission attempts, which reduces the error probability with respect to independent decoding of all these attempts. However, strict URLLC latency requirements limit the use of HRQ. So several HRQ schemes are proposed in 5G specifications and considered in the literature. The first scheme is called reactive. According to this scheme, the user equipment perform a transmission attempt and wait for an acknowledgement from the GNOD B. If the UE receives a negative acknowledgement, it performs a new transmission attempt and waits again. This process continues until the user equipment receiving a positive acknowledgement. An advantage of this scheme is that the user equipment performs repeated attempts only when all previous attempts failed, which provides efficient use of channel resources. However, the acknowledgement process significantly increases the transmission latency. The following scheme is called K-repetition. According to this scheme, the user equipment performs a fixed number of transmission attempts without waiting for any feedback from the GNOD B. This scheme significantly reduced transmission latency. However, the configured number of transmission attempts K can be higher than required to satisfy URLLC reliability requirements. And in this case, the UE will waste channel resource for an extra transmission attempt. The last scheme is called proactive. According to this scheme, the user equipment also perform a fixed number of attempts, but can stop transmitting after receiving an acknowledgement from the GNOD B. These schemes reduces the number of unnecessary transmission attempts in contrast to K-repetition scheme, especially when K is high, more than 4. However, the scheme is not specified in the 5G standard. The performance of the considered transmission schemes is studied in many papers. The summary of the conclusions presented in these papers are shown in the following table. Under the strict latency requirements, when the latency in is about 1 millisecond. The reactive scheme does typically not provide the required packet loss ratio because number of transmission attempts is limited by the delay budget. The other schemes are able to provide required reliability and show similar efficiency in terms of channel resource consumption. Under the tolerant latency constraints, all schemes are able to provide the required PLR. Moreover, the reactive scheme is the most efficient in terms of resource consumption. The K-repetition scheme consumes more resources because of unnecessary blind retransmissions, and the proactive scheme can decrease the number of these retransmissions and hence improve channel resource consumption. The studies show that the considered schemes can be more or less efficient depending on the scenario parameters, such as latency and reliability constraints, network load, user mobility, and others. So the optimal choice of the most suitable scheme should depend on these parameters. When considering the allocation of channel resources, we should divide two essentially different scenarios. In the first scenario, all users transmit packets periodically. An example of this scenario is an Industry 4.0 factory, where autonomous devices transmit data according to the production cycle. In this case, the GNB can dedicate channel resources to all user equipments in advance, so the resources of different users do not overlap with each other. In particular, the GNB configures the dedicated resources and periodicity for each user. Another case is when URLLC application generate sporadic traffic. For example, when autonomous vehicles generate messages about the detected obstacles. In this case, periodic allocation of dedicated channel resources leads to inefficient resource usage because users may not have data to transmit in the reserved time slots. So in such cases, it's more efficient to allocate shared resources to all user equipments. The GNB should configure for each user similar shared resources and set periodicity about 1 time slot. With this configuration, user equipment can start transmitting immediately after receiving data. Note that with shared resources, transmissions of different users may overlap and interfere with each other, which can lead to additional packet losses. Several studies propose a hybrid resource allocation scheme. According to this scheme, the user equipment performs the first several attempts using dedicated resources, and then uses shared resources for additional attempts. This approach allows reducing resource usage in contrast to the case of using dedicated resources. However, the need to use the dedicated resources for the first attempts limits the maximum number of the UEs in the network. Randomization of channel resource selection is an approach to improve transmission reliability. Randomization can be performed at the frequency domain by selecting different resource blocks for different transmission attempts using frequency hopping. Also, randomization can be performed at the time domain by using uniformly distributed time slots. It can be implemented by time allocation from the GNB and random mini-slot selection from the UE. Random resource selection allows improving reliability because of avoiding possible correlated fading and interference. When user equipments use shared channel resources for transmission, the GNB does not know when and where each user equipment will perform its transmission. The GNB should detect which user performs the transmission in each resource element for successful demodulation and decoding data. The problem is complicated by the fact that multiple users can can make transmission in the same resource blocks. To solve this problem, the GNB can use the demodulation reference signals, or DMRS, that each user equipment transmits along with the data. DMRSs of different users are orthogonal to each other, so the GNB can divide the DMRSs of different user equipments and perform multi-user detection. The GNB can use the successive interference cancellation method that improves the probability of successful data decoding when multiple users transmit data simultaneously using the same frequency resources. Let's consider how this method works using a simple example with two user equipments. The first UE transmits data S1. It encodes and modulates it, resulting in signal X1. Then the user equipment transmits in the uplink channel with the channel coefficient H1. The second UE performs the same actions with its data S2. As a result, the G0B receives the sum of the signal Y1, Y2, and epsilon, where Y1 is the H1 multiplied by X1, Y2 is the H2 multiplied X2, and the epsilon is the additive Gaussian noise. According to the successive interference cancellation method, the G0B tries to demodulate and decode the signal with the higher power at the receiver. Let be the signal Y1. If the decoding is successful, the G0B can encode and modulate this data to restore signal X1. Then the G0B multiplies it by the estimation of channel coefficient H1 with hat and calculates the estimation of the signal Y1 on the receiver. This estimation is subtracted from the initial signal. So the resulting signal is the sum of Y2, a component corresponding to the imperfect channel estimation, whose power is typically close to the noise power, and additive noise. So the SIG mechanism allows canceling interference from the more powerful signal Y1, so the G0B can demodulate and decode Y2 with a much higher success probability. This is the end of the first part of my presentation. So if you have any questions about this part, you can ask it. A question from Aleksei Kureyev. The question from Aleksei Kureyev, does G0B estimates channel H1 and H2 separately? Yes. To estimate these channel coefficients, G0B uses the modulation reference signal that orthogonal to each other. The modulation reference signals of different users are orthogonal to each other, so the G0B can estimate these channels separately for different users.
Alexei, I have one more question.
Yes.
So you say that there is a unique reference signal for each user equipment in your network. So is that right? So that no two different UEs have the same reference signal. Is that correct?
No, in general, specifications of the signals that described by specifications of the 5G networks, the number of unique demodulation and reference signals is, of course, limited. And we can say that all users can have the unique DMRS. However, many studies propose methods to increase the number of unique signals that can be used in 5G networks for URLLC. So so this problem is not researched, and I can consider it in my presentation. But yes, it is a problem, and there is many approaches to solve this problem. But in my seminar, I not considered it.
Okay, I see. The last thing I wanted to clarify is the do I understand it right that user equipment do not have any idea that G0B actually uses successive interference cancellation to separate two signals from each other? Let me clarify. Do user equipment use some special parameters? For example, the first user equipment knows that it is the closest and the other one knows it is the furthest. Is there such information on the devices?
I think no. For the considered scheme, they don't need this information because typically it uses the maximum transmission power and that uniformly allocated over channel resources. So the answer is generally not, but I think some schemes that and some approaches that where the users know this information can increase the performance of non-orthogonal multiple access in this case. In 5G specifications, there isn't any methods to implement this.
Okay, it's clear to me now.
Okay, my next section is transmission parameter selection. The performance of the URLLC transmission, which includes packet loss ratio, latency, resource consumption, network capacity, significantly depends on transmission parameters selected by G0B. And my next part of the seminar is devoted to the challenges and approaches for transmission parameter selection problem. Note that in this section, we will consider scenarios with strict latency constraints, where only k-repetition grant-free channel access is the only channel access method that provides to meet latency requirements. So I assume that all devices use this method unless otherwise specified. As I mentioned earlier, when the user equipment use grant-free channel access, the G0B should select and configure the transmission parameter in advance. The channel quality can significantly change in the time and frequency domains due to fading and interference. So if the G0B select parameters based on the instant channel quality estimation, the reliability requirements may be unsatisfied due to possible degradation of the channel conditions. On the other hand, very robust transmission parameters will significantly increase the channel resource consumption. So there is a non-trivial problem. GNB should select transmission parameters, including modulation encoding scheme, number of transmission attempt, and other, in order to minimize channel resource consumption and meet strict URLLC latency and reliability requirements. The basic approach for parameter selection is to select fixed similar parameters to all users. The parameters can be selected using analytical models or simulations. And it's important to know that proposed in literature analytical models are inaccurate because of multiple assumptions. Some of the assumptions are presented on the slide. While simulations require much time because of very strict reliability constraints. In addition, different users can have very different channel conditions, so fixed parameter often correspond to a user with worse channel conditions. It leads to non-optimal resource usage by the UEs with better channel conditions. That's why various studies propose adaptive methods for transmission parameter selection. The following work proposes to select modulation and encoding scheme MCS for each user equipment using a set of the threshold values for received signal power. For users with lower power, GNB select more robust MCS. However, the authors do not propose a method to select these thresholds, as well as an algorithm for selecting the number of transmission attempts. The next paper proposes to adaptively select the number of repeated transmission attempts depending on the fading correlation that depends on the user mobility. With a high correlation, UE should use a larger number of transmission attempts to guarantee the required reliability. However, all UEs use the same modulation encoding scheme that not depend on the distance between the UE and the GNB. And moreover, the authors do not propose a method for selection this correlation used correlation threshold. The authors of the following article proposed a configured grant selection algorithm. In the considered system, the GNB configures the multiple configured grants with the different transmission parameters, and the UE can select the most suitable one based on latency and reliability criteria. However, the adaptive MCS selection is not investigated in this paper. Also, the proposed algorithm does not solve the minimization of channel resource consumption problem, because the algorithm proposes to choose a configured grant with the least latency among ones that satisfy reliability criteria. In our recent paper, we proposed an adaptive transmission parameter selection algorithm that selects both modulation encoding scheme and number of transmission attempts in the scenario when all user equipments use dedicated resources for transmission. The idea of the algorithm is to estimate packet loss probability for all possible combination of transmission parameters, modulation encoding scheme, and number of transmission attempts, using signal-to-noise ratio measurements and error model. After that, the algorithm selects the configuration of parameters that meet the reliability requirement and use a minimal amount of channel resources. We compare our algorithm using the most robust modulation encoding scheme and with optimal parameters founded by an exhaustive search that provides the same coverage as the most robust modulation encoding scheme and minimal channel resource consumption. Numerical results show that the proposed algorithm provide more than 2 times lower channel resource consumption than fixed robust MCS, while meeting the URLLC requirements. Also, it provides close to optimal channel resource consumption. Currently, in our lab, we design and investigate an extensions of this algorithm for a case when all user equipments use shared channel resources. These extensions takes into account possible interference between transmission of different users and usage of the successive interference cancellation mechanism at the base station. Unfortunately, research of this algorithm is not published yet, so I can't describe it in details now. This is the end of my seminar, and the key points of the seminar are shown on the following slide. Specifications of 5G networks introduce many features that enable URLLC in the uplink. However, specifications does not describe how to efficiently select parameters of these features, for example, MCS, number of transmission attempts, and other. Several algorithms are proposed in literature, but none of them adaptively select both MCS and number of transmission attempts. We propose an algorithm that provides close to optimal channel resource consumption while satisfying URLLC requirements for a case when user equipment uses dedicated channel resources. And in ongoing research, we design an extension of the algorithm for a case when user equipment use shared channel resources. This is the end of my talk. Thank you for your attention, and I'll be glad to answer all your questions.
Yes, thank you, Aleksei, for your presentation. I wanted to start with a question from my side. So I was interested in the research that was related to power thresholds. Can you switch to that slide, please? Yes, so you say that the authors do not propose a way to select these thresholds, but isn't the way for selecting these thresholds is simply to estimate them from the thresholds or those modulation encoding schemes? So the modulation encoding schemes have a certain threshold when one can receive them with a relative probability at a certain signal-to-noise ratio. So can we use signal-to-noise ratio for dedicating the thresholds?
In this approach, power on the receiver, this threshold is used to determine the path loss or the distance between users and base station, because it's assumed that all devices uses the same power that depend on MCS, but it much more depend on the distance between the UE and the base station. So if the distance is low, user equipment can use high MCS to consume less resources. and the distance is high, the UE should use more robust MCS. But the problem is that there isn't any algorithm to simple select this threshold. We can use signal to noise ratio estimation, yes, but it's not clear how to select it only at the experiment or simulation, but it isn't a good way to select these parameters. So the problem is that the authors propose the method, but not create the main part of the method, adaptive algorithm to using MCS.
Okay, thank you for that answer. Do we have any other questions for Aleksei? Okay, so maybe I have the last question before the end of the session. Can you please show us your results once again?
Yes.
Yeah, so you show here the algorithm parameter just called window. And can you repeat once again what is it about?
Yes, I'm not says about in the seminar because I described our algorithm very shortly, but I can do it now. The algorithm works in such way: the user equipment periodically sends the pilot SRS signals, and the GNP uses them to measure all signal to noise ratio in all in all frequency resource elements. Then the GNP uses these values to estimate the packet loss ratio for all possible combinations of the transmission parameter. And next, in algorithms, there are some mechanisms. I can show an additional slide. There are some mechanisms that help to if we use the instant packet loss ratio estimation for each pilot signal, it can lead to very frequent parameter change of parameters configuration. So in our algorithm, we create the mechanism that all packet loss ratio estimations for each transmission parameters configurations are averaged using exponential moving average method. This is an exponential window as a parameter of the algorithm. And these results show us that in increase of the exponential window leads to lower channel resource consumption because the transmission parameters are more stable. But if we consider a scenario with very high mobility, using very high window values can lead to inaccurate channel estimation. So the selecting of these parameters is also a non-trivial problem. And in our paper, we propose methods for algorithm parameter selection.
Okay, yes, I see. That's actually very interesting. So the size of your window depends on the speed of the environment changing. Yes, okay. Uh, Maybe any other questions emerged during our conversation? Okay, so I hear no questions and I see no more new questions in chat. Okay, Aleksei, that was an interesting topic. Thank you very much for your talk. And I will welcome everyone to our next telecommunications seminar, which will take place in the next week, Friday. And in this talk, Evgeny Korneev will tell us about his field of research connected to VR applications. Thank you once again, Aleksei, and every participant here. See you next week.
Thank everybody for the attention.